Hello and welcome to Lecture 4 of Charge Separation and Storage in Phys 1204. In this lecture we're going to look at electric field energy, and we're going to have our first serious consideration of circuits. Before I start, I want to remind you of something that we're going to use a fair bit in this video lecture, and that's Kirchhoff's loop law. So I've in previous video lectures made the argument that when we have a fully charged capacitor attached to a battery, then as you go around this circuit from A to B, as you pass through the battery, you see a potential difference as the potential rises in the battery, and then there's no potential difference across the wires because they are conductors in equilibrium. And then you see a potential drop in the capacitor, and you have to get back to the potential you started at, and so the potential difference across the capacitor has to be the negative of the potential difference across the battery. But this is actually just a direct consequence of something we've already seen, which is Kirchhoff's loop law. Remember that told you that if you go around any closed loop, and this is a closed loop, then the sum of all the potential differences has to be zero. And so that's all we're seeing here. One of the things we need to know about is how much energy gets stored in a charged capacitor as it goes from uncharged through charging to its fully charged state. So let's think about a capacitor with some capacitance C, and it's starting uncharged, and so the potential difference across it is zero. And after we charge it by some process, which might use a battery or something else, it has a charge plus Q on one plate and minus Q on the other plate, and some final value of its delta V. But think about the problem with how we're going to think about this. If you take the first little bit of charge and you carry it across to the other plate, probably via some wires, but remember the work involved is path independent. Well, that first little bit of charge didn't have to go through any potential difference, and so no work was done. However, now the plates are a little bit charged, and so there is now some potential difference here. And that means the next little bit of charge that you decide to carry across requires a larger amount of work done. And so what we need to do is set up an integral, since the amount of work done on each bit of charge that's carried over is different. So let's talk about the little amount of work done to carry a little amount of charge, which I'll call delta Q prime. And that we know by definition is negative delta Q prime times the potential difference at that moment. And note that the charge at that moment, Q prime, we know is C delta V. And so this delta Vc can be replaced with Q prime over C. Well, now we're going to sum all of that up to get the total work, although what we actually want is the change in potential energy, which is the negative of the electrostatic work. And so that gets rid of this negative sign, and we are going to have an integral from zero charge to the final amount Q. And that's rather easily done. There are several other forms we can write that in. If we replace Q, we can get it in terms of the potential difference instead, and often that's a useful form to be able to write it. So we've just seen that when the potential difference across a capacitor is delta Vc, the energy stored in the capacitor is given by this formula. And for a parallel plate capacitor, if we just insert the expression for the capacitance in terms of its plate area and plate separation, and the relationship between the potential difference across it and the electric field strength inside, then we get this expression. A little bit of rearrangement and cleaning up with cancellations of factors of S yields this. And what's interesting about this is that it has this AS in it. Notice what that is. That's the volume of the space in between the plates, right? It's the area times the plate separation. That's the volume of a box enclosed between the plates. And that means we can think of this potential energy as an energy density times the volume in between the plates. We're literally thinking of the energy as being spread throughout the space in between the plates with some particular density, which turns out to be proportional to the square of the electric field strength. Notice that this is something new and different. Up until this point, we've really always been careful to talk about energies as being associated with physical objects. But this energy density is now, in some sense, in space, held by a field. So this is a different way of looking at energy. We're still talking about the configuration of the system, but it's not objects anymore. We're thinking about it as to do with the field. Well, we'll see this again when we get to magnetism a little later in the course. We're going to be talking about circuits more and more from this point on in the course, and we need ways to draw quick diagrams of them. Here are schematic pictures, such as I've used so far, of a battery with a charged capacitor. This is already pretty schematic because, while some batteries look like the ones in the picture, many don't, and a capacitor typically looks nothing like what's in the picture. But we need even quicker ways to draw circuit diagrams, and there are accepted ways to do it. Wires are just lines, and junctions, which is where wires meet, are just places where lines meet. But a battery is drawn this way, and by convention in this symbol, the large line corresponds to the positive terminal of the battery, and the small line corresponds to the negative terminal. And a capacitor just looks like a pair of plates. So under this set of conventions, this circuit of a capacitor with a battery would be drawn this way. Often when we draw a circuit diagram, if we know the EMFs of batteries, the capacitances of capacitors, and so on, we'll write them right onto the circuit diagram. A very important thing to realize about circuit diagrams is that only certain details matter. So I've drawn this circuit diagram this way, but I could have drawn it this way and it's showing exactly the same circuit. Or this way, or in some overly, unnecessarily complicated way like this. What matters in a circuit diagram is connectivity. What is connected to what? And all of these diagrams are showing that the positive terminal of the battery is connected to one plate of the capacitor, while the negative terminal is connected to the other plate, and they are connected by nothing more than wire. There's some other terminology we use. For example, things like capacitors and batteries, anything but wires, are referred to as circuit elements. And so we could have a pair of circuit elements, and perhaps they're both capacitors, or perhaps they're both batteries, or maybe there's one of each. And I'm just going to think about two general circuit elements, so I'm just going to draw them as boxes. And we say that these are in series if one and only one end of A is connected to one end of B, and there are no junctions in between them. So this particular pair is in series, but this pair is not because there's a junction in between their ends. And note something about circuit elements in series. Whatever charge enters A here, since it never stops in A, no circuit element ever builds up charge, not even capacitors. Remember, the total charge in a capacitor is always 0, so all that charge has to move on to B. Whereas in the case where they're not in series, the charge that comes into the first element here doesn't necessarily all go into the second element, because some of it could take the path down the other wire at the junction. On the other hand, we say circuit elements are in parallel if both ends are connected and if there are only junctions between the ends. So this pair A and B is in parallel, but this pair is not, because between these ends of them there's this other circuit element C. And note that the potential difference across one must be the same as the potential difference across the other if they're in parallel. Why? Well, it's because of path independence. Carrying a probe charge from 1 to 2, but either through A or through B, the electrostatic work is the same, and so the potential difference is the same. But if you try the same with this set of 3 circuit elements, all you come to is the conclusion that the potential differences across B and C add up to the potential difference across A, and so A isn't in parallel with either B or C. By the way, it's quite possible for circuit elements to be neither in series nor in parallel. In fact, that's probably the most common situation. A, over in this case with A, B, and C, is certainly not in parallel with either B or C. It's also certainly not in series with A or with B or C. Now, suppose we have some fairly complicated system of capacitors like so, and we have a battery that we're about to connect to it. You see, I haven't made the final connections. Well, as we make those final connections, charge is going to move. Charge is going to be pulled through the battery. And so in the end, there's going to be some amount Q1 on capacitor 1, Q2 on capacitor 2, and so on. They will all eventually be fully charged with different amounts of charge on them. And that means that some total amount of charge that I'll just call Q has passed through the battery, which means the battery has done a total amount of work that is just Q times its EMF. Well, suppose we were instead to just have a single capacitor, so that when we connect the battery to it, we get exactly the same amount of charge flowing through the battery, and that all now ends up on that capacitor. And again, the work then done by the battery is the same as in this case. We would then say that these two circuits are equivalent. And one way of thinking about equivalence of circuits is that the battery is doing the same amount of work. And so this capacitor would be the equivalent capacitance to this combination of capacitors. Let's use the idea of equivalent circuits to draw conclusions about capacitors in series. And so in particular, let's start by thinking about this chunk in the middle. Notice something. That chunk of metal is not connected to anything, and it must have been neutral before we connected the battery, and so it must still be neutral. And so whatever negative charge is here is the same as the positive charge here, because all that's happened is it's polarized. And so what that tells us is that Q1, the amount of charge on capacitor 1, is equal to Q2. And that must be equal to the total amount of charge that got pulled around through the battery, and that's Q. So we've just learned that for capacitors in series, the charges on them are always the same, and they're the same as the charge on the equivalent capacitance. Now, to learn something else, let's do Kirchhoff's loop law. So we'll consider this loop, and going around that loop, we have this. And remember that the charge on a capacitor is related to the potential difference across it. And so I can rewrite this all as, which I'm going to find convenient to write this way. Well, if I do all the same things over here, I get this. And since these are the same epsilons, that gives us a relationship between the equivalent capacitance and the capacitances of the individual capacitors that are in series with each other.